Hi everyone, for those of you who already joined, let's just give it a couple more minutes and we'll go ahead and get started. Right, hi everyone, let's go ahead and get started. Let me share my screen. A sec. Lacey, can you confirm that you can see my screen?
Yeah, looks good.
All right. So good morning or good afternoon, everyone, depending where you are. I wanted to invite you to this last meeting of the DOE i2X Forum on Implementation of Reliability Standards for Transmission, or i2X First. My name is Julia Matevosian. I'm an Associate Director and Chief Engineer at IEEE, and we are supporting this initiative from IEEE side. So before we go ahead and get started, I just wanted to remind you that the first half of this meeting will be recorded and will be posted on IEEE website. If you don't wish to have your voice recorded, please do not speak during the call. If you don't wish to have your image recorded, please turn off your camera or participate by the phone. If you speak during the call or use a video connection, you're presumed to consent to recording and use your voice and image. That being said, we are not recording the discussion part of the meeting, so feel free to speak up, turn video on, raise your hand, and participate actively. So first of all, if you have been participating in this before, you know I have this polling question. We are trying to find out what industry sector you are representing. So please go ahead to slido.com, use event code first11, and participate in the poll and indicate what industry sector you are from. It helps us to understand our audience better. It's the last meeting, but still bringing up the goals and outcomes for the i2X First. We are trying to facilitate understanding and adoption of new and recently updated standards relevant for existing and new interconnection of wind, solar, and battery storage plants. The forum convenes industry stakeholders to enable practical and more harmonized implementation of the standards. And yeah, I already mentioned that the presentation portion will be recorded and then the discussion is just free discussion. Additionally, after each of the meetings, we are publishing summary of the meeting where we bring out recommended best practices, challenges, gaps, and required future work. You can have a look. We keep all of the summaries within one document, so you can just open one document and catch up on meetings that you have missed. So just a little bit about leadership team. We have Cynthia Boswell from Boston Government Services. She's a contractor to DOE Wind Energy Technology Office. Robert Reedy from Lindell Reed, who is a contractor for DOE Solar Energy Technologies Office. Will Gorman from Lawrence Berkeley National Lab. Jens Bermer from Electric Power Research Institute. Myself from IEEE. and Ryan Quinn from Elevate Energy Consulting. So usually during this recaps, I bring a summary of the previous i2X meeting. And the previous i2X meeting was actually a half-day in-person workshop that we had in March during our E6 Spring workshop. The workshop was dedicated to conformity assessment with applicable interconnection requirements after commissioning. So after the plant has gone through commissioning and is operational, how do you ensure that the plant is indeed conformant with applicable requirements, be it IEEE 2800 or any other requirements? But for this meeting, I actually wanted to bring up a recap from the December meeting that we had on reactive power and voltage control requirements. And the reason is that today we're having a continuation of this meeting. We were supposed to have it in January, but it got canceled. And so now this April meeting is instead of this one. And since this December meeting has been, a while back, I thought it's more useful to bring up a recap from that meeting instead. So what we talked about there was clause 5 requirements from IEEE 2800 2022 standard. And this is a requirement on reactive power and voltage control. Then we had MISO speak about the phase 2 IEEE 2800 2022 adoption efforts. And so reactive power voltage control requirement was included as a part of that phase 2. And then BPA talked about their voltage control strategies that they apply in their territory. So as kind of opposed to MISO that was talking about IEEE 2800 adoption efforts, BPA just talked about what requirements apply there today and what are best practices that they do with regard to voltage control requirements. And then we had Q&A and structured discussion around these topics that you can see on your screen. And then meeting summary and recording has been now posted on ESIG webpage. And once I'm done talking through this introduction, I'll put a link to the page in the chat. So you can go back and watch the recording of this and all other prior i2X first meeting, as well as look at the summary document if you missed any of the meetings. So just some key themes that were raised during this December meeting. The first one is on adoption of 2800 2022 clause 5. The implementation of the clause requirements can help clarify and refine existing voltage control requirement and can aid reliable design and operation of the IBR plants moving forward. There was a conflict that was indicated between fork order 827, where some system operators are not fully leveraging the requirements of IEEE 2800 2022 clause 5 due to conflicts with fork order 827. And this is particularly related to utilization of reactive power capability. So 2800 requires rectangular reactive capability, while fork order 827 requires triangular shape curves. And this may be leading to underutilization of IBR reactive power capability requirements and results in costlier transmission reinforcements than may be necessary. Then reference point of applicability voltage control is the most common way of control is voltage control, so not constant reactive power, but on voltage control mode for BPS connected IBRs. And 2800 2022 includes specifications for performance targets for this type of control, including reaction time, maximum step response time, and damping ratio. Selection of group and deadband settings based on local BPS needs and transmission operator voltage control practices can also help improve grid reliability and stability and increase transfer capability in some cases. And so this was something that BPA extensively brought up in the meeting and talked about their best practices and experiences with using voltage group for voltage control. And system strength should be accounted for when determining performance requirements for voltage control for an IBR. So I just wanted, because this is the last meeting of the season, I wanted to bring up the schedule of the meetings that we had. I will not read through it, but you can, we'll post the slides after the presentation. You can have a look. We started in May last year. And as I mentioned, this is the last meeting. We had 2 hybrid workshops, so in person and online. One during ISIC fall workshop and one during spring workshop. And those were focused on conformity assessment. So we were looking into kind of getting a sneak peek into 2800.2 recommendations. As I mentioned, we post now all of the materials on ISIG website. So we basically moved all of the previous recordings and slides to ISIG website, and going forward, we'll be posting recordings and slides and meeting synopsis on that webpage. And I believe Lacey already put the link in the chat. So you can go ahead and look at that. Just to mention deliverables from the season 1, as I mentioned, we post slides and recordings after every meeting. We post summary notes summary notes you can see on the right-hand side right now on the screen. We're also running a survey. We're trying to understand, if people like the format, if they have any suggestions. And I will put the link for the survey in the chat once I'm done talking. So please take a minute and fill in the survey. It will not take more than 5 minutes of your time, but it helps us to improve our future meetings. As we are finishing season 1 of the i2X first meetings, we are already planning season 2. There was supposed to be a 1 month break in April, but because January meeting got canceled, now April is taken, so we'll just continue on with season 2. You might have seen an email already that went out with season 2 announcement and registration. And again, I'll put a link for this in the chat where you can register for all of the meetings or just select the meetings that you would like to attend. These are preliminary themes, so we are again continuing the topic of standards, but this time is digging deeper into adoption best practices, into conformity assessment. We'll continue following NERC milestone 3 standard development efforts as they are following up on FERC Order 901. And so we'll be bringing up these topics and any kind of, questions and controversies here. So to bring it to people's attention as they comment on the standards. And then during, towards the end of the meeting series, in December, we also ran a survey for, what are the topics of interest, and people already indicated that they would like to learn more about grid forming and inverter-based resources. So towards the end, we'll spend maybe a meeting or 2 on grid forming specifications, and hopefully we'll have a hybrid event in March during ISIC Spring Workshop that is dedicated to grid forming specifications, testing, and lessons learned from existing projects already. And again, you have links to sign up. I'm seeing Lacey already posting those in the chat. So you can, again, as I said, sign up for the entire series or pick meetings that you're interested in and sign up just for those. We'll continue posting the materials on ISIG webpage. And again, we'll be doing recording slides and we'll start a new synopsis document so that, we have one for each season. Just one additional thing I wanted to bring up. This is not related to i2X first specifically, but is related to IEEE 2800.2. The content of 2800.2 we agreed within the working group is ready for balloting. And so ballot pool is open until May 2nd. And you can, if you are a member of IEEE Standards Association, you can sign up for the balloting pool. So basically what it entitles you is to review standard, provide comments, and then participate in ballot. If you are not a member of IEEE Standard Association, you can still join it. It's very inexpensive. So if you're interested in looking at 2800.2 and participating in balloting and commenting, I encourage you to join. And I'll put a link in the chat as well so that you can do this. And as I mentioned, you only have now 3 days left to sign up. So this deadline is just to sign up for balloting pool. There'll be time for review and comment period. So more instructions here. You can just see it from the slides. will not spend time on this. Before I go into, just give me a second, before I go into agenda for today's meeting, I also wanted to bring up on Jens's request, EPRI is also starting a cross-sector initiative on application of IBR standards, and it's a collaborative forum, and they are scheduled to kick off tomorrow at 2 p.m. Eastern time, and I'll put a link to that in the chat. So if you're an EPRI member and interested in participating in this, join that meeting as well. All right, so just for today's agenda, as I mentioned, we'll continue talking about reactive power and voltage control requirements. I've already done my introductions. So as I mentioned, in December meeting, there was a lot of interest from people to learn more about Vars at night, or maybe Vars at zero output. And so I heard about, Amin Noor from EPRI has done extensive research in this area. So we invited him to present here. So he'll go first. And then we'll hear from Alex Lee from ORCOT, and he'll be talking about communication of capability and status of online inverter-based resources that have 0 megawatt output. And then you'll hear from Divya from Ørsted, and she'll be talking about reactive power and voltage control requirements and developers' perspective on it, because previously in December meeting, we were talking about what are the requirements and what is the system operators or transmission owners' perspective. So now we'll hear kind of from the other side, from the plant developers, and what are challenges and opportunities there. And then, as always, we'll follow up with Q&A to all of the presenters, and then transition into structured discussion, and again, talk about these topics on implementation of voltage control requirements, Vars at 0 megawatt, and then if time permits, I have another topic for discussion about reactive power and voltage control and how utilization of these capabilities can be optimized. So with that, and without any further ado, let's go ahead and move on to the presentations portion. Again, just assume there's good rules of conduct, be respectful, but please ask your questions and be active in the forum. And your opinion matters, and we would like to hear from you as well. And with that, Amino, I turn it over to you.
Sure. Can you confirm that you can see my slide deck?
Yes.
Okay, perfect. Thank you, Julia. Thanks for the opportunity to share some of our research results and findings in this meeting. As Julia mentioned, my presentation focus will be on solar PV inverters, and the primary target is can solar PV inverter provide reactive power support during nighttime, or basically when it's not generating active power. That's the focus of this research. Our group at EPRI is primarily focused on the high penetration of renewables, impact on the distribution circuit. So, and I primarily focus on the technology side, so smart inverters, laboratory testing, field demonstration, model development, model validation, and also the standards, but primarily IEEE 1547 standard activities is my primary focus. Actually, Julia already mentioned that she saw me making this presentation in Copenhagen in 2023, and then she invited me also to present in ORCOT meeting and also for Tutus meeting. So I just wanted to disclaimer that some of these materials I have presented before. If you have attended those meetings, you may have seen it, but there may be some new materials also there. So just want to make another comment is that my presentation is primarily focused on the technical capability side. My primary question is, can solar PV inverter provide reactive power support? So that's the technical side. But of course, there's a lot of importance on the business side. Who pays for it? Is it economic to get it support from the inverter-based resources, or you use your traditional equipments, regulators, and StatComs, other devices? So those are very important questions. Those has to be addressed before it becomes a full-fledged real-life operation and utilization. But again, just to help you to orient my presentation, my talk today is primarily focused on the technical capabilities. Can it do it? If it does it, can it do it seamlessly when it transitions from daytime to nighttime and then wake up in the morning during sunrise? And also what it costs. So cost here I'm talking about to provide reactive power support. the PV inverter or the PV plant will need some active power. How much is that active power? It's coming from where? So those are the kind of research questions that hopefully will be to a certain degree addressed in this presentation. But motivation side is, of course, we are having high penetration of intermittent generation sources like solar and wind, which maybe sometimes some part of the day can have excess generation, pushing the voltage high. And with the growth of EV charging, and also what is happening in the data centers, there could be huge load. Certain time the load is also high, which can reduce the voltage. So what I am saying is that, or I'm envisioning is that there'll be more voltage fluctuation happening on a day, both from high voltage and low voltage direction. So we need to have resources that can address or help to address those challenges. And again, since my work is more on the distribution focus and voltage issues are typically on the distribution side, so that's why I'm saying that maybe distribution system operators will have more challenges to maintain voltage regulation. And as many of you know, both 2800 for IBR for transmission connected system on 1547 on the distribution connected system now make this reactive power capability and certain control functions, reactive power-based control functions, mandatory in this standard. Utilization is not mandatory, but capability is a requirement, both standards. So even for distribution connected resources after 2018 standard is now mandatory. However, this is the one difference between 1547 and 2800. Right now in the 1547-2018 standard, there is no requirement or there is no minimum requirement that the DER has to provide any reactive power support when its generation is below 5%, not even 0%, not even nighttime. So if the generation falls below 5%, there is no minimum requirement. Again, the standard does not say anything about that it cannot do it. So it's not a prohibiting it, but it's not a minimum requirement. That means it's not a guaranteed availability, capabilities available from the certified inverters. But today I'll show some of the example results that what we have seen from laboratory testing and also field demonstration whether PV inverter can do it or not. So that's kind of the background and motivation. So what I'll start with the two examples of individual PV inverters that we tested in our lab to see what we have observed there. And of course, then I'll switch back to some field demonstration results or findings that we work with one of the utility in California. So first, I'm talking about a product that we tested. It's a relatively old product. It's basically shown in the left side, in the figure on the left. The inverter that you're seeing there is from inverter, I would say at least 8 to 10 years old inverters. So it's even before 2018, 1547, 2018 standard. So we are testing this inverter for some other research. Then we also see whether it can provide reactive power support. And that triggered our interest to explore it further. And we have a lab in Knoxville, Tennessee, where we do all kinds of inverter testing. So first of all, since this is not a mandatory requirement, it all depends on whether the product is offering that capability or not. And how do you activate that capability? By default, this capability will not be active. As you know, most solar PV inverter, almost all solar inverters goes into sleep mode during the sunset or when irradiance falls below a threshold. They stay off or in sleep mode whole night. In the morning, when irradiance goes up or DC voltage goes above a threshold, it wakes up and starts generating power. But if we want this plant or inverter to be available to provide reactive power, then we have to figure out whether the capability is offered by the inverter and then how to activate this capability. So this particular inverter has a function called or setting called reactive power output at night. So I'm just copying from the manufacturer settings profile. We have to activate that, and we have to activate that before it goes into sleep mode. So during the daytime operation period, you have to activate that. So that's what we did. And then we basically try to mimic a middle of a day, noon to next day noon period, and if irradiance going from top or maximum to the zero, stay in the nighttime and then waking up. So this orange curve mimic the irradiance profile of a whole day, but we squeeze that into a 1 hour period for running testing in the lab. So we used a PV simulator where we uploaded this irradiance profile and the output DC power was fed to the inverter to see how the inverter operates to that. The blue curve is showing the active power generation from the inverter, and we commanded the inverter to absorb 20 kVAR during this test period. So the command was go to active power absorption mode, and the target was 20 kVAR. So what we wanted to do, two things. One is, can it do it? Of course. The second part is, can it do seamlessly? Like when you transition from daytime to night and then wake up at night to daytime next morning, is there any interruption? Is there any period where it's not providing the reactive power support? So those are the main two objectives. And then of course, we also want to capture how much active power is actually need during the nighttime to stay on and provide the reactive power support. So that's kind of another thing, but I'll cover that more details in the next slide. So what you are seeing, basically the active power, of course, from 31 kilowatt gradually goes to 0. And during this night period when irradiance is 0, active power is close to 0, but actually not 0, it's a negative. I'll explain that next. But then next morning it wakes up and go back to the normal operation. But if you follow this orange curve in the middle, the reactive power throughout this period was constant. So it did not interrupt, it did not drop, it just provided that capability. So that's the first answer, that yes, it can do it. Of course, if it offer that capability and if you configure it correctly, it can do that, and it can do pretty much without any interruption. And what we have seen for this particular inverter is that to do that, it was absorbing roughly 328 watt. And again, it's a 33 kilowatt inverter. We are absorbing 20 kVAR. So the inverter itself was absorbing or importing 320 watt from the grid. So this is what I meant by cost. It's not free. So this active power has to come from somewhere. Somebody has to pay for that. So those are the business side discussion. So then we wanted to say, okay, not just one target reactive power. What if I vary the reactive power demand? What if it's not just absorbing, but also injecting? So basically operate this inverter into fixed reactive power mode, but we should define target reactive power value. And for each of the tests, we captured how much real power or active power it takes from the grid. So that's the plot you are seeing on this in this screen right now. So that's one type of voltage control function where some other entity may command issue to the plant that, hey, give me this much of var until I provide you next command. But what if you want to do plant or inverter operate autonomously? You can load a volt-var curve. So that's what is shown on the inset figure on the right side. We provided a volt-var curve, which is, I think, no, it's a modified version of the IEEE 1547 category B volt-var curve, or not the default one, it's a modified one. And basically, then we use a grid simulator to change the voltage, go from low voltage to high voltage, and then bring the voltage back to the low voltage. And for each, we took a continuous recording of the reactive power absorption in response to the voltage variation. That's the plot you are seeing on the right side. And again, high voltage inverter was absorbing VAR, low voltage it was injecting the VAR, and the VAR went all the way up to 20 kVAR, or maybe a little bit higher than 20 kVAR. And for each of those reactive power value, what was the active power consumption from absorption by the inverter? So that was captured. Again, these numbers varies a little bit, but in general, just to keep the inverter operating 0 VAR, it takes around 35 watt just to stay on so that it can provide reactive power support, 35 watt. And then roughly, again, it's not exact number, but roughly for each kVAR, it was taking 14 watt. So these are the numbers we wanted to get out of this test, that what is the cost if it wants to stay on, how much active power is needed. So that's the result for this particular inverter. We have seen it working and it can do that. Then more recently, we tested a new inverter, which is actually IEEE 1547-2018 certified, or 1741 SB certified. If you're familiar with the distribution side requirement, that's the requirement. And this particular manufacturer offered this capability again, and they have a white paper or some description in their website, explains how to do it. So again, we have to find out what is the setting and how to activate that. So this particular inverter, our OEM calls it reactive power for 0 active power. The names are all over their own description since it's not defined in the standard. I'm talking about 1547. And also in that mode, you can turn it off, which is by default off, but you can also turn it on and then select which control mode needs to be operated. So we selected the QV, which is basically volt-var function. But again, one thing I have to highlight that for both inverters that we tested, this setting has to be activated when it is operating. So basically daytime operation or solar generation period, you have to activate them, that will continue to operate. If not, it will go to sleep mode, the low irradiance condition equivalent to sun nighttime. So again, we configured that. Then we configured that with the volt-var curve shown on the left side, which is basically 1547 category B default setting. And after that, we basically did the same thing. From low voltage, we went to high voltage, and then bring the voltage down, make slow changes, fast changes, different types of tests. And then we captured the reactive power output from the inverter and also corresponding active power demand. So one thing I like to highlight here, that if you see the red dot, If we let the inverter to go to its typical sleep mode, like sunset, you can go to sleep mode and come back in the next morning, it was taking roughly 4.9 watt. So this is a 50 kilowatt inverter. During nighttime sleep mode or standby mode, it takes 4.9 watt. But if we activate this function, Q at 0 active power, basically nighttime VAR, it was taking roughly 139 watt. So you can see clearly a change. There is a active power demand, whether you not get any reactive power out from the inverter, just to keep it operational, there is a cost, like roughly 135 watt additional is needed just to keep it on for the whole night. And then the more VAR we request, whether absorbing, injecting, the more real power is needed. It's not a perfect linear curve. So, but we have seen roughly, again, similar 14 watt per kW. We cannot generalize that that will be the case for all the inverters, but so for 2 inverters that we have tested, there just to keep it on, there's a different magnitude of active power needed. But then for the VAR, we have seen roughly 14 watt per kW for both of the inverters that we tested. So far, that's the individual inverter performance from our lab testing. I know most of you are transmission side of the business, so your interest might be more transmission connected, bigger IBR plants. So that's what I'm going to cover next. This is a project that we did with LADWP in California. It's actually transmission connected 90 megawatt solar PV project or plant. It's connected to 240 kV transmission system. There are some details there, but the main thing is that there are 32 power blocks. So each block is 3 megawatt or 3.3 megawatt roughly power blocks. 30 of them were equipped with a 3.2 MVA central PV inverter. So these are big central inverters. Each of them are 3.2 MVA. So that's kind of the 30 out of the 32 power blocks. And one block has a smaller string inverter, so 100 kVA string inverter, which is something similar to what I have shown before, the string inverter that we tested in our lab. And the other one was a different research component where you have a DC coupled PV plus energy storage. But we activated this this reactive power support testing for the whole plant, the entire plant. So first objective was, can it do it during nighttime? First question. And if we have a different magnitude of reactive power demand, both in injection absorption direction, can it do it? How accurately it can do it? How much time it takes to go to the target Q value, those kind of a question. And I intentionally highlighted that, yes, some individuals during this project periods are actually issuing command in the midnight. So 12:30, so anywhere from midnight to even 2:30 a.m. in the morning, they actually run this test. And thanks to them, we have the results now. So what we have seen that, yes, there is some delay once you issue the command, depending on which value, which direction we are asking the plant to provide reactive power support, it can move from somewhere between 10 seconds to 24-second response time was involved there. And remember, the command was issued to the plant controller, and then plant controller was issuing command to the inverter. So of course, there is some communication delays there, but roughly somewhere between 20 to 24 seconds were needed for the settling time. And in terms of accuracy, it was somewhere between, I would say, 0.3% to 1.2% accuracy or error was there compared to target values and actually what was absorbed or injected by the plant. So that's the first level of verification, can it do it or not? Then the second question is, again, the same thing, that to keep the plant operational, how much active power is needed? And for this particular project, there was a compensation also provided to the plant owner or plant operator for that active power consumption. But again, this is a research project, so don't tie that to a business decision here. And also, if we have increasing amount of reactive power demand, both in the absorption, injection reaction, how much active power is needed? So what we have seen, if we let the plant go into sleep mode, like this is default settings, it was taking roughly 317 kilowatt. Again, this is a 90 megawatt plant. So 317 kilowatt was the demand if this traditional operation where plant goes into sleep mode. But if we keep it operational so that we can do reactive power support, no matter whether fixed VAR or volt VAR, that's different, but just to keep it operational, it was additional somewhere between 600 to 700 kilowatt was required, additional to compare to the sleep mode. So that's the first question. So plant has many inverters. Transmission connected plant have 2 levels of transformers, like each power block has its own medium voltage transformer. Then you have a high voltage transformer. Then of course there are long AC cables or AC collection system throughout the plant. So there are losses or losses in addition to the whatever active power the individual inverters need to keep operational. So that's why we cannot just multiply the inverter power by X and then get the total plant active power requirement, because plant has other components there also. So again, this is one example of a real plant doing it and how much it costs to do it there. Then once we have the some level of conformance that yes, it can do it, then the main thing we wanted to do, can it do it seamlessly for several days, basically continuously. So we have run the test in 3 buckets, 8 days, 10 days, 6 days. We configured the Volver curve as shown on the picture. And again, this is 240 kV target. So based on what was the utility requirement as a target voltage, we configured the Volver curve accordingly and wanted to observe how it does. So that's the configuration was provided to the plant controller, and then we collected the data and analyzed it. So what I like to play, and hopefully it will work, is a small video for a day from maybe early morning to the end of the whole day, when the active power and reactive power changes, corresponding voltage at the POI. And also on the right side, you are seeing a blue dot is moving. So basically it's a time-lapse video of measured voltage and reactive power changes happening. Julia, can you confirm that you can see the video? Is it working?
It works.
Okay, so thank you. I was not sure about the speed. So you can see most of the time is following the black line, which is the configured Volver curve. But every now and then you'll see it will switch, or it will jump to a non-curve value and then try to come back immediately. So I'll talk about that in the end of this presentation. But the main conclusion is that pretty much throughout the day, it was following the setting was provided to it, with few exceptions where it was off from the target. And you can clearly see voltage goes high, it is absorbing VAR, voltage goes low, it is injecting VAR. So it can provide the support in both directions. And if you see the time on the top, on the left side figures, this is from midnight to kind of a next day midnight. So 0 to 24 hours. So not just only daytime period. And green curve clearly shows night, daytime, and then again night period you are seeing there. So every now and then, when there's a sudden voltage step change, that may be something else happening on that circuit. Some other regulation device are taking action. So that may be one reason that it goes off and then comes back. And sometimes we also have seen this particular plant, some communication issues or some not ideal operation or perfect operation happened. I'll talk about that at the end. Okay, so that's kind of an example of one particular day. But now if we analyze the entire test period, like total 40 days of testing, maybe, 18 of the test days and 22 of the baseline days where we let the plant go into sleep mode and no reactive power support from there. So you are comparing, seeing the comparison of voltage profile for test days, which are green, and baseline days, which are blue. And you can clearly see when the days when Volver function was active, voltage was tighter, the spectrum of the voltage was tighter and more centered around the target value of around roughly 240 volts compared to the non-stand baseline days where there was no reactive power support or voltage control support from the plant, the blue curve. So that's kind of an overall shows is over the period, like over 18 days, it maintained the voltage much tighter compared to without any control or support from the plant. And you're seeing more distribution of, okay, to do that, how much reactive power is actually absorbed or injected by the plant? Is it always 30 mVAR or 20 plus mVAR? So our conclusion is that most of the time, so almost 60% of the time, the reactive power demand was less than 5 mVAR. So remember that during that band, no reactive power absorption or injection, only it's absorbing a reactive power when voltage goes high, outside the dead band, whether high or low. So over this test period, I think roughly 22 days, the total consumption, if you plot it, 60% of the time it was below 5 mVAR. But few occasions it went all the way to 24 or 25 kVAR as mVAR, and this particular plant has a limit of 30 mVAR. Is the technical limitation or the contractual limitation? The last thing I wanted to highlight, and this is something important, this particular plant, when it was designed, constructed, I don't think the nighttime reactive power was in the scope. It was maybe an afterthought for a research purpose. And again, We did it for a couple of months and then stopped it and went back to normal operation. So it was not get-go designed for the nighttime reactive power support, but the inverter selected for this project had the capability and utility, like LAWP worked with the plant owner to come up with a project scope and activate this capability there. But what we have seen during this project period, some incidences where you have some communication issues, whether inverter is not responding to the power plant controller or power plant controller is not functioning properly. Some incident happened, and I'm showing one example of that in the around 4 a.m. time period. It was not communicating for a certain time. We have also seen some issues when the plant goes from daytime to nighttime, basically during sunset, when it has a switchover mode of control. Again, these are manufacturers' proprietary things. They did not disclose all the details, but it has some challenges to maintain the transition seamless. And again, this is because this project was not get-go target for this application. So that, but as we show the other inverter testing we have done in lab, it can be seamless. So one thing that I wanted to highlight for this is that if this is a scope, then it should be thought through properly, work with the manufacturer, the contractor to configure the system all correctly so that it can operate the way we want it to operate. But the couple of key takeaways, yes, if the right technology is used, if it's in the scope of the project, the solar PV inverter can provide reactive power support in nighttime, but there is a cost. There is a cost in terms of active power demand to keep the plant operational, whether it comes from a source inside the plant, some sort of UPS or small batteries, or it comes from the grid. That has to be factored in. Who pays for it? That has to be the business decision, has to be covered, but it's possible, technically it's possible. To provide 24/7 voltage regulation support, seamless without any interruption. Of course, it has to be designed and configured correctly, like whether you have to activate that before it goes to sunset, can it do seamless transition? Those has to be properly designed and configured. And to my extent, based on the field experience, if we want the system operators to rely on this type of technologies, then it has to prove its reliability. So it has to operate pretty much all the time, not randomly, not operate certain hours, then you cannot rely on this type of solutions. So that's why I meant that there has to be more proof of concept, more demonstration to demonstrate that it can do it. Then hopefully that will build the confidence of the system operators to rely on this type of resources. I think that's my last slide. So I'll stop here. And I believe, Julia, the questions will be at the end, right?
Yes, thanks so much, Manu. Yeah, the questions we'll keep to the end. If you already have a burning question, you want to put it in a Slido rather than asking, you can do that too. So go to slido.com and event code first11. Also, go to the poll there and indicate what industry you are representing. We are trying to poll people to understand our audience better. And with that, we'll transition to Alex. Go ahead, Alex. You can share your screen and introduce yourself and go ahead. I can see your screen, but I cannot hear you. I'm not sure if you're on mute.
Good morning, everyone. My name is Alex Lee. Can you hear me?
Yes.
Okay. So I'll continue the discussions the presentation we just had and kind of give a system operator perspective of what we have been seeing over the past 7-8 years. So my presentation will kind of go through the issues, reliability concerns, system operators had identified in real time, and what were different thought process we went through to come up with how we're gonna resolve those reliability concerns. So we have some action items that has been taken in the short term and resolved, as well as some of the action items that are still ongoing and more of a long term. Just a quick high-level overview of the ERCOT. ERCOT serves 90% of the Texas load, serving over 8 million of customers. We had a peak demand of a little over 85.5 gigawatt in 2023 during the summers. On the upper right, it shows the generation capacity by fuel type in 2025, which shows we have a little up close to 23% of wind, 19% of solar, where we have pretty high penetration of both solar and wind. The middle right section shows the energy actually that was used by different fuel type in 2024. Capacity factor for solar is a little lower. So although we have 19% of solar install capacity, we actually only got 10.4% of energy from solar in 2024, shown in orange, versus wind actually had 24.2% of energy that came out of it. Lower right just shows a sort of like a historical capacity increase on just the solar since 2010, which was the first year we had 15 megawatt of solar generator come to the ERCOT footprint. Starting 2017 is where we saw more than 1 gigawatt of solar in the systems, and ever since then we've been seeing exponential growth in the solar. And there has been a lot of challenges we have been having with solar, especially during the nighttime when there's not much megawatt output from the solar, and solar plants are unable to provide proper reactive support. So the initial problem we saw was the rules we have at ERCOT is all generators resources should provide the voltage support service and regulate voltage at the point of interconnections. However, some inverter-based resources, including and especially solar power plants, experience megavar oscillations at very low megawatt outputs, and that triggered ERCOT to sort of start investigations of a root cause analysis, because we were starting to see these type of issues popping up in multiple areas in the ERCOT footprints. One example is shown here, would actually happen in April 20th of 2021. This happened, the oscillations of up to 50 megavar happen on a 100 megawatt solar units, which cause a voltage swing of 3 to 4 kilovolt kV on the 130 kV systems. So the chart shown here, the top lane is the megawatt, where the trend shows about 2-hour time frames. And then in the morning before the sunrise, there's not much megawatt output from the top lane, but then because of that, it's showing a lot of megawatt oscillation in the second lane during those time frames, and that causes voltage to swing in the bottom pane. Because of that, we try to assess the impact or the severity of the problem, and we send out what's called a request for informations to a lot of the IBRs in late 2019. Back then, we didn't have as many number of IBRs as we have now. So it was sent to about 130, 150 wind farms, as well as about 13 solar plants. The findings we had based on the RFI was that many IBRs are not capable of providing reactive power at 0 megawatt output. The bar chart here shows on the left only about 54 wind resources that they are not capable of providing reactive power at 0 megawatt output, versus 28 out of roughly 150s that they are able to provide reactive power at 0 megawatt. On the right bar chart for the solar, most of them, about half of them, said they can provide the reactive power at 0 megawatt output, and 2 that they cannot provide it when there's no reactive power output. The caveat and the gray ones that show that's not applicable is more related to grandfathering of a lot of the old legacy technologies, especially on the wind. ERCOT started having wind resources all the way back in early 2000s, and there were a lot of grandfathering clauses where legacy technologies did not have a lot of capabilities. On top of that, even when IBRs responded yes, that they can provide the reactive power, the 20 wind resources and 6 solar resources shown in the green, they said although they can provide, it will cost additional amount of money, or also have to work at OEM to set that up. So it's not, even if they said yes, a lot of them were saying it's more of a potential capability they are not providing that currently. So, and even And as mentioned in the previous presentations, many facilities are already consuming real power from the grid when they're at 0 megawatt output, either which requires for a lot of the auxiliary demand they have to serve within the facilities. So with that, ERCOT looked at a couple different solutions, worked with market participants and stakeholder forums to come up with new requirements to clarify what are the responsibilities for different generator IBR resources that on their voltage or reactive power requirements. When we assessed this problem, we kind of looked at what would be a reasonable requirements for the market participants that own and operate the assets, and without, I guess, imposing a punitive requirement that will sort of have a significant financial impact to them. So similar to how other technologies are, whether it's a nuclear or coal or gas plant, a lot of the resources generators have what's called a low reasonability limit where, until that megawatt point is reached, the plant is not stable yet and it cannot provide full service to the grid yet. So ERCOT decided to try to go that route and apply more similar along that line to the IBR resources as well. So the focus in the short term has been, if the IBR resources are not able to provide the reactive support at the 0 megawatt output, then they should simply reflect that capability in their model and have those information correctly delivered to ERCOT. That way, there's no gap between what ERCOT information has versus what is actually capable in the field. So for the first bullet in item number 1, if the IRR cannot provide the reactive power at 0 megawatt output, they should set the low sustainable limit or low sustain limit to non-zero megawatt, but not to exceed 1 megawatt. Furthermore, once they make that changes, then or reflect their capability correctly, then they should submit or update their reactive capability curve, the D curve, to correctly to ERCOT. Lastly, in real time, when they're having 0 megawatt output, they can just simply turn off the AVR and they can desynchronize the inverters if they want to. So on the right chart kind of shows a high level overview of this, where before these new requirements, they may have had the LSL at 0 megawatt, but with this new requirements, the IRRs are able to increase that LSLs to up to 1 megawatt. So it could be 0.1 megawatt, 0.5 megawatt, depending on the facility. On the lower right is reflecting how the D curve typically looked before this new requirement, where all the D curves started at 0 megawatts, showing both the leading and lagging capability. But then with these new requirements, ERCOT sort of requested or required resources to correctly reflect their capability, and which basically ends up shifting the D curve to the right a little bit. So what has been the impact of these new requirements? And the main goal of this has been to minimize the reactive power and voltage oscillations on the system caused by the current equipment limitations. Because whenever the oscillations happen at a very low megawatt output, the voltage on the transmission systems can swing several kV, as I showed you in a couple of slides ago. But there are other implications, such as providing the accurate and consistent capability of the generator to the system operator, like ERCOT. Without the correct informations, the systems, all the studies that we perform in our footprint may not reflect the correct reliability concerns, and it may not show potential voltage issues that's actually happening in the field versus what our EMS energy management system shows up in our systems. On top of those new requirements, ERCOT started utilizing a oscillation detection tool provided by EPG vendors almost 10 years ago, starting almost 10 years ago. Currently, over years, ERCOT has been increasing the number of PMUs in our footprints. And currently, we have about 270 PMUs that are streamed at 30 samples per second. And this is more for situational awareness and then triggers investigation as needed and when oscillations happen. So on the upper right panel, we kind of categorize different type of oscillations that the system's monitoring, whether it's a frequency oscillations or voltage angle or magnitude oscillations or islanding oscillations or generation trips. And then we also have different locations that are shown in the upper left, where it shows a lot of green bars, which shows the locations, which indicates the location of the PMUs in the ERCOT footprints. And then whenever there's oscillations that are detected, then it will have this type of yellow pop-up showing, okay, at this time point and this specific locations, the detect oscillations has been detected. That way, our engineers can go in and further look at what kind of oscillation is detected by the systems. So this example is a megavar oscillations at a solar PV that are interconnected at a nearby substation. So for this one on the lower right shows the megavar reactive power, which shows a up to 30-40 megavar of oscillations, which reflects voltage oscillations in the middle upper panes. And another thing to note is this oscillations actually did not happen during a low megawatt output, meaning close to 0 megawatt output. Lower left pane shows the megawatt, and it does show about 100, little over 100 megawatt of injection that the solar panel is having. So although the ERCOT investigations and new requirements and rules started for oscillation issues that happened that were observed at close to 0 megawatt output, as we started digging in, there seems to be a lot more oscillations for different type of coming from different type of reasons. So one of the ongoing efforts that we have at ERCOT is with that new requirements, ERCOT is still striving to receive correct reactive capability from all the IRRs, including IVRs. At night, many solar resources still show reactive capability, but they are not responding to the voltage changes in the system. So for this example from 2022, August 9th, it shows about a 7-day time frame where you can see the top blue line shows the megawatt where during in the morning the solar megawatt ramps up, and in the evening solar megawatt ramps down to 0 megawatt. And in the middle pane, it shows the actual megavar output from the solar in the middle line, and then the maximum or upper and lower capability of that reactive capability of that resource showing in green and sort of like a turquoise in the middle lane. What we can notice here is whenever there's a 0 megawatt output that's happening in the middle sections in between actual megawatt output, we see sort of like a flat lining of a megawatt response, sort of not responding at all. Although the voltage in the bottom lane is showing changes throughout the time. In addition, ERCOT is also working on a couple different efforts over past couple years. As I mentioned on the second example, oscillations events seems to be not limited to just megavar output, megavar oscillations at 0 megawatt output. We have also seen quite a bit of megawatt oscillations on IBRs. We also seen megavar oscillations at non-zero megawatt output. We also saw some simultaneous oscillations on both megawatt and megavar happening at the same time, as well as other type of oscillations such as self-synchronous resonance. To better address these issues, ERCOT has created a new team called the Event Analysis Department about in 2022, 2023 timeframe, where their sole responsibility is to perform investigation on multiple different type of system events that are happening in real time, including this type of oscillations. Just in 2025, ERCOT identified at least 13 oscillations event, 10 of which came from solar plants, 2 came from wind plants, and 1 came from ESR, energy storage resources. So over time, we are seeing more and more number of oscillation events happening in the systems. One, because ERCOT has been putting more resources into it, more engineers are looking into this type of and trying to find these type of events and perform analysis on it. And second, we are having more and more inverter-based resources that are being interconnected to the ERCOT system. So what are some of the lessons learned? Some oscillations are fully resolved through tuning or equipment adjustments, which typically take months of interactions with not just the generator owner, operator, but also the OEM vendors for the plant. For the short term, ERCOT's focus has been to reduce the number of oscillations that occur on the system due to equipment limitations, and as long as ERCOT has a right information and right capability is submitted by the resources, ERCOT requirement only extends to that level. IBRs need to work with OEMs to achieve LSL at 0 megawatt or as close to 0 megawatt as possible if they have such limitations. So even if we allow them to not able to provide the reactive response at 0 megawatt output, a lot of the newer interconnected resources tend to have a learning curve where they'll have to work closely with OEM to try to minimize their LSL, where they have a better or wider range of megawatt output where they can provide the reactive capabilities. So this requires controller and inverter tuning and tighter operational margins. And as of April 2025, now still 97% of solar and 100% of wind generators are showing a 0 megawatt low reasonability limit, and ERCOT is still working to get better information from all the resources in the footprints. In the long term, ERCOT would sort of aim to have a stable voltage control provided by these IVRs at full megawatt output, including 0 megawatt output, but that discussion needs to be happen more down the road, and there's a economic impact and market impact to it, and that kind of discussion is still ongoing on what is the right solutions to get that, and whether it would be a reasonable or a set or a goal that makes sense for every market participants. That's all I have from the ERCOT system update, and I guess I'll pass it back to you, Julia.
Thank you so much, Alex. Very interesting presentation, and I see a lot of questions in Slido. I would like to encourage people to use Slido for questions and also participate in the poll and indicate what industry you are representing. And we'll move on to Divya, and we'll take questions after her presentation. Go ahead, Divya. You can share your screen. It's not yet coming up if you're sharing. And I cannot hear you. Not sure if you're speaking. Okay, the screen is coming up. I can
So,
yeah. And
can you hear me?
That's great. Yes, hear and see your
perfect.
screen.
Yes. Yeah, thank you so much. I think a lot of things were covered by Alex and Aminul, my previous panelists. I'm going to give a slightly different perspective on capability and utilization. And the context I'm picking is going to be slightly different. It's going to be more focused on large gigawatt scale plants that likely have a transmission asset that actually provides reactive power capability. So before I start, I'm Divya, and I've also been working very actively with Julia on the 2800.2, and we've had some great discussion, and thank you, Julia, for organizing this. So Orsted itself, a little bit of background, we are renewable energy developers. We have both onshore projects, and we are heavily focused on offshore in the Northeast. And in the context of offshore, most of these are gigawatt scale plants that are being constructed today. So let me just go to the next slide. And really, I would like to touch upon what really capability means and how we are looking at it from a developer perspective, and give an overview of some of the standards and grid codes out there, and give a little bit of perspective on how things look from an IEEE perspective and also the European TSO perspective. And I want to point out some fundamental differences between capability and utilization, and given sort of a feel for what costs look like. I think it was very well touched upon by Emmanuel and also recognized by Alex that cost is something that we have to pay if we have to utilize that. There's another aspect I do want to highlight as a developer and also as a plan designer, what we have been seeing and what we believe would be helpful from a transmission and a ISO perspective to get that information is also understanding what does the grid need and when does it need. And I'll just quickly glance over some of the FERC orders and really try to see where we are missing some information and where we may need support from the system operator and the TO. So jumping through the slide, so the reactive power capability, basically it's a plan must be designed to be capable, and this is defined in plan design documents, or you could reference a standard like the 2800 standards, and most of this is a part of the EPC contracts or the vendor contracts that we sign off on. So if it's not included, there is no guarantee that a plant performs. So it cannot be retrospectively applied. In some cases, we may get lucky, but in many cases, especially today, it's very likely that the plant may not be able to perform if it's not designed from the get-go. So this also means all the controls and equipment are all built in. And this is a fundamental prerequisite for plant performance. Again, I just want to emphasize, so it's a part of the design decision. And if you don't decide to have this capability, then it's not going to be likely to exist, especially in large transmission connected assets. And going back to the 2800 standards, I think one thing I just wanted to highlight here is the 2800 standards also has different requirements based on the technology type. This was just recognizing the technology capabilities that is available as of date. Things could change, things could evolve. But today, if we go back and ask the vendors and the equipment manufacturers, typically at type 3, you may not get any reactive power output at 0 active power. And you may be able to get for some of the others full capability. And you could also define it in terms of voltage, and it's also been done in the 2800 standards. So again, it's important to recognize that most of it was also a compromise based on the technology type the plant uses. So it's not necessarily just the grid needs there. Another shift in perspective, if you look at reactive power capability in Europe, so the NTSOE gave this black rectangular box as a boundary and suggested each TSO or transmission system operator to define their own PQ capability within those boundary limits. And each system operator, based on their transmission or grid needs, they define their own. And in case of Denmark, you can actually see it's also reduced reactive power requirement at active power beyond 80%. So again, this was solely based on their transmission system condition and the transmission grid needs. And there are systems that don't want you to generate or absorb reactive power during 0P. But there are also systems like Ireland and the UK where they do want you to participate, they want these plants to participate. And in most cases, these are all transmission connected large IBR plants. So let me move to the next slide. So the cost, I do want to touch upon this a little bit. And the example I'm taking is offshore plant of 1 gigawatt. And most often for the offshore wind plants, we don't expect reactive power to be exported or imported from the offshore turbines just because of the cable capacitance and the distance. It doesn't make it cost effective, and it does not utilize the cable ampacity very well. So it's always found to be more cost effective to have an onshore transmission device like a STATCOM, and if it is a DC connected offshore wind plant, we would use the onshore converter station to operate like a STATCOM and provide the necessary voltage support. So this is somewhat of a clean case where you don't actually have to look at losses from the cables and other equipment. You can just look at onshore equipment. And in most cases, these onshore substation is located very close to the transmission facility or the POI where it's connecting. So those small AC line losses can be neglected, and we are just looking at the transmission connected equipment. For a typical HVDC system, the converter station losses could be as high as 1 to 2%. And if you look at it from cost perspective, especially in some of the markets where the energy prices could be high, you're looking at least about $1 million per month if there is no wind in that month and you want to run this facility as a STATCOM for only the onshore converter station as a STATCOM, you're looking at $1 million per month. And for a STATCOM, you're looking at about $200,000 a month, assuming that you've sized your STATCOM to just meet today's requirement, which is basically 33% lead lag. So it's significant, and this does not cover for many of there's lots of assumption that's gone into these calculations. It does not cover for the market, actual energy market variations we may see. These are average prices and these are forward-looking forecasts. So there could be changes from this. And also this does not cover the fact that the equipment might be run more than what we anticipated, even when there was no wind. So the wear and tear that may be there is different now with this. So the way we think about capability is capital cost. So you need this hardware and control, and we design it for it. And that makes a lot of sense because it's something we cannot go back and fix. You cannot go back and rebuild a HVDC system or rescale that easily. You need extra real estate space, you need permits, so fixing is always hard. Utilization, on the other hand, you have to think about what is the purpose of doing this. What's the purpose of keeping it active when there is no wind? And some questions we've had, again, given that reactive power is a very local phenomena, it's unclear to us as a generator operator when and where this would be needed. Maybe we are in a location in the electric grid where we are electrically far away from where the reactive power needs are, and we don't know what time of the day it's needed. And it's super important because there may be situations where there's a line that's been taken out of the system, and maybe we are not that effective in meeting the reactive power demand because with that line outage, or maybe the short circuit is so low that our device really cannot stay online. So there are many scenarios where we did not anticipate certain things, and we realize as we move into the transmission network and try to provide some of these, that may be challenged or we may not be that active. And having pretty much was wasting a lot of energy that the grid might have needed. And some aspects that would be helpful, I think it's more a dialogue between the GOs and the transmission owner operator and the system operator. Just understanding the cost of keeping generators online and what are the design boundaries. We also source equipment from the OEMs, so we need to have some clarity on the design boundaries. So what short circuit ratio was it fundamentally designed for? And also understanding, I think Alex did a fantastic job going over some of the control interactions and the slow oscillations they were seeing in the ERCOT grid. It's super important to understand what was the controls tuned for, what short circuit, what is the response time, what was the speed of these controls, so we know if this would be appropriate for a certain condition. And accounting really for different speed, response speed and control response times is super critical in ensuring that these are most effective ways of providing reactive power and voltage support to the transmission grid. At the end of the day, I think it's very important to look at society costs and understand if we are operating the grid in a suboptimal manner. It's not just looking at whether it's cost effective for a GOP, or a transmission owner operator. It's for all at the end of the day. And it helps if we could all get together and understand when, where, and how much is needed. And if there is some transparency on from a planning perspective on where are the absolute needs for these kind of reactive power support. And again, just a little bit of perspective for Carter. I learned from Julia that markets are out of this discussion, but looking at the trend.
Yeah, you're breaking up a little bit. Maybe you can turn your camera off.
Looking at
too.
where focus headed, there's definitely a focus on reactive power capability for IEEE. So let me do that. Now you're better? Hello, can you hear me better?
Let's see. I can hear you now.
So from okay, perfect. So from a Carter perspective, we've been focused on defining reactive power capability, which is fantastic. That gives certainty. Having these standards and clear defined requirements is always fantastic for a generator developer. It helps in designing them upfront and really fixing them later on because the grid requires something. So that's a fantastic first step. And also recognizing that the technology exists today has pushed FERC to be more firm about that. So starting in 2016, it was mandated that every non-synchronous machine or non-synchronous plant must provide reactive power capability. And then I think the latest FERC Order 904 talks about compensation and getting rid of that compensation. I think in what's been missing, and probably so rightfully so, it's not within the FERC scope, is how, when, and where reactive power support is required. This is probably more within the transmission system operator or the ISO scope, and defining that clearly and more uniformly across different regions would be super beneficial. So we could understand where exactly the plants would need to stay online and provide the support and when. So we also want to ensure that it's not a false sense of hope, because if the short circuit is really low, it's important to understand that a lot of this equipment will trip. And because it was not fundamentally designed for that. So having those kinds of information is super valuable. And I think I will conclude from here. So before mandating reactive power utilization, I think it's better to answer the question, is it the most optimal for the society? Is this the only way? And is this a cost-effective manner for the society? Can we find better ways of providing this? And from a grid and transmission system operator perspective, really understanding when and where the service is required the most. And also trying to understand if there are any undesirable interactions that might lead to other types of instability issues, and really more transparency about the needs and will help the industry to innovate. It's not that we don't want to do this, it's just that we don't know much about what we should be doing. So I think anything that can be shared in that context is fantastic. And with that, I'll stop and thank you so much, everybody, for listening in today. And thank you, Julia.
Thank you, Divya. Thanks for interesting presentation. I think it's really nice here that we got different angles kind of on the same topic. I really enjoyed that. So let's transition to the Q&A. I mean, I have structured discussion questions. We have about 37 minutes left until the end. I will prioritize, I think, Q&A questions. Some of them kind of hit on the same questions that I had for structured discussion. So let's do that first. The first question is for Aminul. In addition to additional real power loss, what is the impact of 24/7 voltage support on loss of life in the inverter?
Yeah, that's a very good question. Definitely, we have heard from the inverter manufacturer that there will be some impact on the expected lifetime of the system. Most PV inverters are typically factored in for 10 or 12 hours of operation per day. And they factored in that there'll be 10 hours of sleep time. So that's what is mentioned. But I don't think it will be a linear approximation that will half or something like that, because you are not operating at full current or full power. The heat generated inside is not same. And I have heard one presentation in Europe, the workshop that we attended together, that basically this operation actually helps. I don't know if there's the proof of that, but because of not getting cold or others, it even helps to improve the life expectancy of the devices. So I would say this definitely need to be investigated. There will be some impact, but may not be as like a double or half the life of the system, not like that.
I mean, I remember hearing, maybe it was at the same workshop, people also talking about life of transformer, that, the transformer is supposed to be used half the time versus, using it full time if you provide reactive at night. Do you have any information about that?
I'm not an expert of transformer reliability, but my common sense saying that transformers are typically like load transformers. They're operating 24/7 for the whole life, right? So compared to PV plant, which are like 20, 25 years lifetime, inverters that could be 10, 15 years lifetime.